Okay, so welcome everyone to my presentation on exploring metrics for the analysis of code submissions in an introductory data science course. So I like to start by noting that data science is an emerging discipline whose transformational values are recognized by many agencies and organizations. More than anything, the job market reflects how much of a demand is needed for data science practitioners nowadays. So in response to this trend, many universities and organizations have begun offering data science courses, and this comes in many different formats and flavors. So for example, here is a list of departments where you can expect to find a data science course offering across different universities. And this is not surprising because data science itself is a very interdisciplinary domain that intersect with computer science, math, and also specific domain expertise. So that leads to the question of how can we support students learning of this complex skill set? And there's a lot to explore about this question because most of the prior work on data science education has remained at a high level of curriculum discussions and case studies of course design, whereas our goal is to promote a more data-centered approach to evaluating and improving data science courses. Towards this goal, we definitely should look into prior research in computer science education because in the past decade, there has been a similar explosion in enrollment to introductory CS1 courses from students with a variety of backgrounds and not just those in technical fields. So in turn, this phenomenon has led to a rich body of research on student modeling and support, covering many different aspects such as classroom activities, student performance, teaching theories, and automatic assessment of code submissions. Now, among these points, we would like to focus on the last one, which involves auto-grading and code metrics. And the reason is that coding is an integral part of learning data science, just as it is with introductory programming. Yet at the same time, there are similarities and also differences between computer science code and data science code. So you can see one example on the left and one on the right here. So we are interested in what these similarities and differences are, as well as how they influence the evaluation of students' code submissions in a data science course. So in particular, using code submission data from an introductory course project and a set of coding metrics, we seek to answer three research questions. The first is how do the metric values vary across the different tasks in the project, and how do they compare to the solution code metrics? The second question is how do the code metrics relate to the submission runtime? And the third question is which change in code metrics is indicative of a change in submission score? So through these questions, our goal is to examine whether the chosen metrics can reflect the nature of data science code as well as the student's learning progress. To answer these questions, we collected data from 2 semesters of a graduate level Intro to Data Science course. The course has a conceptual component with reading assignments and quiz, as well as a practical component with 5 individual Python coding projects. Each project spans 2 weeks and consists of 10 to 15 tasks that the student needs to implement. So here is a screenshot of an example task, which asks the student to implement a recommendation algorithm. Students are given the task description and a template function, which they need to fill in. We should also note that all the coding projects are auto-graded, so students can submit any number of times to an auto-graded system, but there is a limit on the code runtime as well as the external libraries that students are allowed to use in each project. After making a submission, the student can get the auto-graded feedback after a few minutes, which includes the grade for each task, the stack trace, and any mismatch between the student's output and the reference output. So in this work, we focus on submission data from project 1 only. This is an introduction to the 3 standard data science libraries, NumPy, SciPy, and Pandas. The context of the project is that students are given a data set of 100,000 movie ratings, then they need to perform basic data manipulation and implement the collaborative filtering recommendation algorithm. For this project, our sample size includes 97 graduate students from 6 different programs. They made a total of 1,107 submissions, 14 of which were excluded from analysis because they had compile errors. There were 113 full score submissions from 76 students. Here we note that a student might continue to submit after getting full scores if they want to further optimize their code, which is why there are more full score submissions than the number of students. So here are the set of metrics that we use in our analysis. The first is Halstead volume, which measures the size of space necessary for storing the program. The second is Cyclomatic complexity, which measures how many linearly independent paths there can be through a program. The third is logical line of code, which measures the number of executable segments in a program. The fourth one is AST node count, which measures the number of nodes in the abstract syntax tree representation. The fifth one is library call, which measures the number of calls to functions and methods from external Python libraries, which in project 1 are limited to these 3, NumPy, SciPy, and Pandas. Finally, we have solution library call, which measures the number of library calls that also appear in the solution code for a project, where we get the solution code from the course instructors. So we should note that the first 4 metrics here are those used in traditional software engineering, and they have also been used by previous research on CS1 code analysis to analyze students' progress. So roughly speaking, they reflect the complexity of the students' code, whereas the last 2 metrics here are those custom metrics that we want to experiment with. They don't necessarily reflect the size of the program, but instead more about the strategy, for example, which function the student choose to use. So first we look at the distribution of metric values. So we see that among the 113 full score submissions based on the histogram here, there is actually a wide variability across the different submissions. So this means that there are notable differences across students, even though their submissions were all at the completion stage of the project because they got full score. For example, based on the logical lines of code distribution, we saw that some students only wrote 80 lines for the entire project, whereas others took more than 160 lines. So there's like a lot of variation in the solution space, which is interesting. So to understand what these differences mean in terms of student evaluation, our next step is to build regression models from the chosen metrics. However, we first wanted to identify any internal correlation among the metrics themselves, because if a group of metrics had a high degree of correlation, then they could be considered as conveying the same information, and we will only need to select one from that group for subsequent analysis. So here's the pairwise metric correlation. So based on this histogram, we select the correlations that are larger than 0.6 because we think these reflect high correlation. So these are the ones highlighted here. What this means is that library code, AST node count, and logical line of code, these 3 are highly correlated among each other. And so in this group, we will only need to pick one metric moving forward. So our final set of metrics includes the Halstead volume, the cyclomatic complexity, the library code, and the solution library code. So based on these 4 metrics, now we compute the coding metrics for each individual task in the project. So there are 12 tasks here. Here you can see each point on the line graph indicates the mean metric value at a given task. And the shaded region indicates the 95% confidence interval of the metric distribution across the student submissions. So the line here is for the student, and then we also indicate the metric value of the solution code at each task in the big red dots here to facilitate the comparison between what the solution looks like and how the class is doing. So we see that for the first three metrics, Halstead volume, cyclomatic complexity, and library codes, while the line plots have different patterns, they all have peaks at task number 6 and number 11, which imply that to students, these are the more complex tasks in the project. The solution code metric for task 11 is also high. So this task was indeed intended to be challenging. On the other hand, if we look at task number 10, then we see that the solution code metric is pretty low, but the student code metrics are pretty high. So there's a notable gap here. So when we asked the instructors about this, we found that task 10 can be solved by simply applying the function from task 9 to a different input, which is why the solution code only contains one line. However, most students did not realize this connection, and instead they implemented this task from scratch, which is why their code is much more complicated. So this is a case where the code metrics can help the autograder to provide more specific feedback that points students to the connection between task 10 and task 9 here. Finally, we look at the plot for solution library codes. If you recall, these are the number of library codes that are used by both the solution code and the student. And we found that in most tasks, only about 30 to 50% of the library codes are in common. So in other words, students were able to solve the project task with many library codes that were not used by the solution, which indicates that there can be many different strategies to solve the same task. So in summary, from these four graphs, we have identified variations in the coding metrics across tasks, where task 11 could be considered the most complex. At the same time, there were notable gaps in the code metrics between the student and the solutions implementation of task number 10. To better understand these metric differences, we next examine their relationship with the outcome of each submission, which can be measured by the runtime as well as the score. So for RQ2, we look at the runtime first. From the 113 full score submissions, we constructed a linear regression model where the independent variables are the four metric values of each submission, and the dependent variable is the submission runtime. From this, we found that library code is a positive and significant predictor of the code runtime. In other words, when the number of library code increases, the runtime also increases, whereas this relationship is not as strong with the other metrics that we have here. For the third question, we look at the score. So one thing we want to note here is that we don't want to use the metrics to predict the actual score, because the score will depend on whether the student's code passes the test case or not, and that information is not reflected in the metrics alone. So instead, we want to change perspective, and we look at when the student score does change, which coding metric also changes along with the score most consistently. In other words, which metric can be most reflective of the student's progress throughout the project. So to answer this question, we built a mixed effect model where we predict the change in score based on the change in each metric. Here we note that because each student makes multiple submissions, so they contribute multiple data points, and so we want to use the student's ID as the random effect. This factor can be considered as a representation of each individual student's coding style. For example, one student may change multiple function codes in one line, while another student may have a separate output for each function call. So these different sizes would lead to different baseline values of the matrix, which the random effect can account for. So our results show that the library code is once again a significant positive predictor of the change in submission score. So in other words, when the student has more library codes, then it is likely that their score also increases. So our work, to summarize, our work investigated the coding metrics of student submissions in an introductory data science course as a first step in connecting data science education and programming analysis through examining a combination of traditional software engineering metrics, which are Halstead volume and cyclomatic complexity, as well as data science specific metrics, which are library codes and solution library code. We have identified the metrics that are indicative of the task complexity, the submission runtime, and the submission score. And here we will further discuss how these findings highlight the distinctive features of data science programming and how they can contribute to providing instructional feedback in an introductory course. So first, we observe a wide variety in coding metric values, even among the full score submissions, which are all at functionally equivalent. This diversity highlights a key difference between data science and introductory programming, which is that the solution phase of a data science task can be large, even if the task is well-defined with a fixed correct output, such as those that we use in this project. This insight is further supported by comparing the student's code metrics with the solutions. For example, we saw earlier that the distribution of solution library codes remain low throughout the task, indicating that even when project one was intended to teach students about data science libraries, the codes that they chose for their implementation were largely different from what the instructors had anticipated. While prior research in introductory programming has typically used the distance between the student's code and the solution code to measure their progress, our findings indicate that such an approach may not be effective here because students might perform well even when they took different approaches from the solution. So it is still possible that deviation from the solution can still be a meaningful metric, but they should be measured at a higher level than the code content. Might be getting towards like the conceptual or the strategy that the students think when they choose a certain approach. At the same time, we found that identifying notable gaps between the students' code metrics and the solutions can also guide cost improvement strategies. In particular, if most students' code has lower metric values than the solution code, then students likely make use of a shortcut that the instructor did not anticipate. So in response to that, we should either redesign the task to prevent this shortcut or adjust the score weighting to account for the lower than expected difficulty. At the same time, if the student's metric turns out to be a lot higher than the solution metric, which we did see in our analysis, then this is indicative that students were doing more work than necessary, and it leads to an area for providing adaptive hints and feedback that can guide them towards the correct solution. So in our next analysis, we ran a linear regression model to examine how each coding metric contributed to the submission runtime. We identified a library code as a positive and significant predictor of the submission runtime. We believe that this effect can be explained by the vectorized nature of the library codes where they each operate on the entire data set. So because there are 100,000 rows, if we process over these multiple times, then naturally that would lead to higher code runtime. Another measure of submission outcome that we investigated is the output score, because we want to see which change in coding metric closely align with the change in score when the student score did change. So to this end, we set up a linear mixed model, and we found that library code is once again a positive and significant predictor. So this finding highlights a similar observation from an interview study by Cross and Gore 2 years ago. In their study of how data science practitioners taught the subjects, the author noted an emphasis on connecting existing API to shape them for the task at hand, rather than implementing custom functions and classes from scratch, which is more common in introductory programming. We believe that this is a very notable difference between computer science code and data science code, which was proposed by Cross and Gore and also empirically validated in our study. So what this means is that an important learning objective for data science novice is to acquire fluency in common data science APIs. And we believe this is a valuable insight for instructors. So as a first step towards exploring the value of coding metrics, our work has certain limitations that we plan to address in future studies. The first is that to create a meaningful context for metric comparison, the analysis so far has focused only on a subset of the submissions to one project. So for the next step, we would like to investigate the full submission story of each student in order to identify those who need additional support in the course. Second, we plan to collect data from other data science courses at different institutions to validate the generalizability of our findings. And third, we should emphasize that data science is very interdisciplinary, where the nature of code in one subdomain may be very different from code in another domain. For example, a project on web scraping would place less emphasis on factorized operations, but more on text parsing and cleaning. So it is important to examine each subdomain separately, but also identifying the core data science thinking components that can transfer between subdomains. And finally, we should note that as demand for data science increases rapidly, universities and organizations are actively expanding their data science course offering. However, our research indicates that a more evidence-based approach to teaching and learning data science is needed due to the distinctive nature of the domain. So in particular, we found that the number of library codes rather than traditional metrics used in CS1 courses is more reflective of student progress. And we believe that identifying other suitable metrics is an important step towards refining the learning objective and curriculum design. We also show that comparing the metric values of the student code and the reference code can reveal which tasks are easier or harder than expected, which further adds instructional revision. So these results in turn lay the foundation for follow-up work on implementing data-driven and timely interventions, which would ultimately contribute to a scalable workflow for personalized student support in data science education. And that is the end of my presentation. Thank you for your attention.
All right, thank you very much. We have a couple of keen questioners waiting. In fact, we've gone a little bit over time, so we only have about 4 minutes before the next keynote. But I'd like to invite Yang Shi, if you are still present. Would you like to unmute and ask your question?
Definitely, yes. Yeah, I don't know. Yeah, sure. So basically, I just want to ask are all the students from CS background, because basically, if you are in a CS course setup, students from different backgrounds will just perform pretty different in the data science courses, right? So you assume that students from a CS, they would have some kind of like training on the how to code, and for students who who is not from CS background, maybe they will just struggle at the start of the course. So would you, based on that, would you just suggest that we give some guidelines of how to code to students with mixed backgrounds? Yeah.
Okay. Thank you for your question. So the students come from 6 different programs, and they're not OCS, but they are own STEM. So we have some students from electrical engineering as well. So I would say that the current analysis and results is definitely more biased towards the technical students who likely have some prior coding experience. So it would be interesting to see how students from like business or psychology background would do in the course, which is one of the points that I mentioned in the future work. That is like, we will need to look at more course data to verify how general the findings are.
Yeah, definitely, because my university is trying to do a data science initiative that accepts all kinds of like different backgrounds. This will be a very interesting topic to look into. Thank you.
Right, thank you.
Great, thanks for a good question. And I see that Insong Zhang has also got a question. Are you still there, Insong? Would you like to speak?
Yep, I can speak with the second question. So when this question is statistically based, so if you look at the RQ3 and the RQ2 results, I'm having issues regarding the selected metrics interpretation, because based on the definition of selected metrics, the number of linearly independent paths and executable statement are all positive values. So what is the interpretation of the negative number appearing in the result for 95% confidence intervals in both the linear regression model result and the mixed model result?
So the linear coefficient here just indicates a negative correlation. So when the student's code has more Halstead volume, which basically means they have more variables and operators, it turns out that their code runs in fewer time, which is a bit surprising, but we should note two things. First is that the coefficient is not very negative, it's close to zero. And one possible interpretation is that like if you save each of your intermediate computation in a variable, right? As you go through the task, then that means you would avoid having to recompute those when you need them later. And that means your code runs faster, but at the same time, your code has more variables. And that is why that could explain the negative correlation here.